When we add an acid to water, the acid is going to act like an acid and donate its proton to the water. And so we end up with A minus and H3O plus, where the A just represents the part of the molecule that is not the proton that's donated to the water. This reaction is called an acid ionization reaction. And typically, this is an equilibrium reaction, so it occurs in both directions. Let's take a look at the molecular level at what's happening when we have an acid in water. If we have an aqueous solution that contains a little bit of acetic acid, then that acetic acid molecule, which contains an OH on the one side of the molecule, so we have an OH group here, can bump into a water molecule and transfer that white hydrogen to the water. And that leaves behind this acetate. Let's watch it one more time. Here comes the acetic acid. There's the OH, donates the H to the water. The water leaves as H3O plus, and we have this acetate anion, which is the acetic acid without the hydrogen on the oxygen that is attached to the carbon. We said this reaction can happen in reverse, so let's watch that reaction in the reverse direction. So notice that we have our acetate molecule here, and it can encounter an H3O plus, and the H2O plus can transfer a proton back to the acetate, forming HA, or acetic acid again. When those two reactions, the forward reaction to donate a proton to the water and the reverse reaction to donate a proton to the A minus, happen at the same rate, this reaction comes to equilibrium, and we have an equilibrium constant that is designated by Ka for the acid ionization equilibrium constant. Like all equilibrium constants, the magnitude of K will tell us something about the tendency of this reaction to go in the forward direction relative to the reverse direction. And so if we have a Ka that is large, then the reaction tends to make mostly products at equilibrium, and we mostly have the ionized acid, the A minus, and H3O plus in solution. However, if Ka is small, then we have mostly reactants at equilibrium. Now remember that by large, we mean approximately Ka bigger than 10 to the third, and by small, we mean approximately Ka less than 10 to the minus 3. When we have an acid that has a large equilibrium constant, where we pretty much dissociate all of the acid, we call that a strong acid. So a strong acid dissociates completely and has a large Ka. However, a weak acid is one that has a small Ka and does not completely dissociate. It's important to note that strong and weak acids are defined by the value of their equilibrium constants and not the concentration of acid that we put into solution. When we have a highly concentrated acid in solution, we say that it is concentrated. So a concentrated acid is not the same as a strong acid. So you can have a strong acid that is concentrated, but you can also have a strong acid that is not concentrated, that is dilute. And you can have a weak acid that is concentrated or a weak acid that is dilute. Recall that a base, which I'll just designate as B, in aqueous solution can accept a proton to become BH plus and form OH minus in solution. So the definition of a base is something that produces OH minus in solution or accepts a proton. This reaction, as for the acid ionization reaction, occurs in both directions and has an equilibrium constant equal to Kb and is called the base hydrolysis reaction. All the same concepts apply to this reaction as to the acid ionization reaction. So we'd say that a base is strong if it has a large Kb, and we say that a base is weak if it has a small Kb. And again, concentrated bases can be either strong or weak, and dilute bases can be either strong or weak. So concentrated refers to the concentration or the amount of base in solution and is not the same as being strong.